Hi guys, welcome to the Advanced Refrigeration Training Podcast. I'm your host, Kevin Compass, along with my partner, Brett Wetzel. Today's episode is sponsored by Westermeyer Industries, the leaders in oil management and pressure vessels for the commercial refrigeration industry. Whether you're involved with designing a system or tasked with servicing one, Westermeyer Industries has been helping meet the needs of customers like you for the past 20 years. They offer a broad catalog of stock system components with an in-house team of engineers to assist with custom solutions as well. From oil separators and heat exchangers to system monitoring devices, Westermeyer Industries are a total system specialist with industry expertise, engineering know-how, and the manufacturing muscle to help you tackle problems and deliver solutions.
Hi, guys. Welcome to the Advanced Refrigeration Podcast. I'm your host, Kevin Compass, along with my co-host, Brett Wetzel. And today we're going to go over VFDs, why we use them, and a couple schemes of how we use them in condenser control applications and some compressor applications and some other fan motor applications. So Brett's going to start us off on. We're going to start off on condenser control applications and different ways to set these VFDs up and why we're doing them certain ways and not others. So you want to take it, Brett?
Yeah, I want to hear about your week, though. You said you had a really interesting week this week.
Oh, so yeah, this week we're doing some Novar control changeouts, and this is my fifth one of these, and they get worse every time. This one was a rough one. There was a lot programmed wrong, so it was just a nightmare of trying to figure things out. Things don't match prints. Prints are just suggestions. It was kind of a royal pain. I mean, I was really hoping this one was going to go easy because the last couple were somewhat easy, but yeah. So I spent most of my last 2 days with another guy crawling around our bellies, readdressing cases because somebody messed up and changed all the addresses on all the single deck cases. So we had to pull, apart like 25, 30 cases and readdress them.
Fun.
So makes for a real not fun week. What about you this week, Brett?
I finally got the communication issue taken care of. On top of having, after a remodel, they had a star configuration. Then they had another star configuration to a wire that just went nowhere. And then they had another star configuration that had been there on the Spectrum network that had been there, forever. And then on another set of cases where it was supposed to end, they just had a random rogue wire that just went off to nowhere. I did some training this week. We did some like Rack 101 stuff. And I am going to a facility that makes a certain kind of powder. And they have had, I think, several contractors out there. The guy right now is using temporary cooling, and he's been so used to the equipment not working that he's basically spending a bunch of money every month just to keep it running with temporary equipment. It's basically a Heatcraft piece of equipment, condensing unit connected to almost like a Deskin type machine. And they keep taking out compressors, keep having oil failures. They do have some sort of controller controlling the suction pressure. That's all I know. I know they have lots of floodback. They've taken out many a valve plate. And the only other thing that I'm thinking, because I've seen something like this before. When I was up in Pennsylvania, I took care of a chocolate plant. And when I first took over the account, they're like, oh, by the way, this piece of equipment usually ends up taking out the compressor at least twice a year. I'm like, why? And they're like, we don't know. They've changed pulleys, they've changed sheaves, trying to figure out what the hell was going on. They changed expansion valves. They went too small, then they went too big. Then they tried going to the right size and then trying to file down the pins in hopes that they could do like a mid-size expansion valve. Long story short, I was standing in front changing the filters at a big filter wall. I almost got blown off by the air that was coming out the duct. So I tried something. I started, I'm monitoring the superheat and started breaking off the The distribution grill superheat went from 4 degrees to 6. Started breaking more stuff off. Went up to 8, broke more off. Went up to 12, and I just took the whole thing off. And basically, the discharge grill, wherever they had it connected, was restricting the air so much that that's actually what was causing it. And superheat, instead of being up at the unit, was supposed to be at least above 20 degrees. It had always been somewhere in the wheelhouse of 8, and forevermore it's been 28, and they haven't changed the compressor out in a couple of years now. So win for me. So I'm hoping this is like a similar situation where it's just basically some kind of crap restriction somewhere. But I guess I'll find out. I'm going out there tomorrow morning. So tonight we're going to be talking about VFDs. First, we're going to go over the temperature control, TD control, which is usually how most condensers are being controlled. If someone didn't listen to the terminology podcast before, TD is basically, when we're speaking of condensers, we're basically talking about the temperature difference between what the ambient is and what the saturated condensing temperature is. So, for example, if the condenser has a TD of 15 degrees, basically if it's 100 degrees outside, the saturated condensing temperature means the drop leg pressure converted should be, approximately, 115 degrees. Typically on rack refrigeration, you're for anything low temp, anywhere from 8 to 12 degrees. Medium temp stuff is usually like 12 to upwards of 17, can be up to 18. Single systems and split systems typically have a TD about 20 degrees. Just to throw that out there, even though you're not ever going to see a VFD on a single system, but basically, you get a lot more better control using a VFD. VFD uses AC voltage and basically makes a sine wave, but it actually pulses what's called DC voltage. They do pulse width modulation. So basically, it's pulsing DC voltage in a positive and a negative to basically make a sine wave out of a whole bunch of little square waves. And that's basically how a VFD is doing its job. It's basically, it's saving money because, your control is not starting and stopping fans all day long. You have better pressure control. So it's a lot more smoother of a transition. And just saves money because you're cleaning up your signal going to your motors. Now, one of the things you do have to be concerned about when using a VFD, if it's something that you're putting a VFD on, you have to make sure that the insulation on the motor windings are rated for a VFD. They have motor ratings. Motor winding ratings going from A to, I want to say F. F I think is the last. I'd have to be 100% positive on that. I know they do have an X for
F is
a
VFD rated.
Yeah, so F as the basically the more heavier duty windings, because basically you're slowing down that fan, so you're not moving as much air across it. So the windings have to be able to take that excessive amount of heat that you're actually putting through that winding. So anything you want to add, Kev?
Yeah, I still see a lot of like motors come out and start up. Even from manufacturers like Crack, they're notorious for putting non-F motors in condenser coils and slapping a VFD on it, just sending it out the factory. So even though that OEM motor may not have that insulation class in there, but if you're changing a motor, I would recommend that you put a VFD rated motor back in. Like a US motors, like Verispeed motor, those are great motors. And the other thing, like Brett didn't mention, was is a lot of these motors don't have ground bushings on the shaft. So a lot of these motors that fail, like Brett was just talking about, they're not F rated. Well, even those F rated motors can still have issues with bearing induced currents on the shaft. And what happens is you get this bearing induced current on the shaft, and it pits out the bearings, causing little arcing. So there's shaft grounding rings you can put on these motors. Some motors are already tapped for them, like the US motors. They sell a kit for them. I generally try to put the shaft grounding rings on if I'm changing a motor. It's cheap insurance for, compared to changing another $500 motor again. You see a lot of bearing failures on drive changeouts after like drives are retrofitted. You see a lot of bearing failures, and most of those bearing failures they're not from the the motor spinning slower. They're from bearing induced currents that are causing like arcing on the bearings when the VFD's moving.
So I saw something today on an old drive, and I was trying to figure out whether we should keep it. We were flipping from a Commander SK to a 9-deck M400, and we were trying to figure out. It looked like almost like a buck-boost transformer, but basically it was on the I believe the incoming side of the VFD. It was like a sign, like something that was supposed to clean up the sine wave a little bit. You know anything about them?
Yeah. So yeah, that's a oh man, just it's a choke coil is what I've always heard referred to as. It's basically to help clean up the power a little bit coming into the VFD. Provides like a little bit of voltage protection too for like a spike or something. But yeah, you should have a choke coil on most stuff. I mean, if it's got a drive on there, I mean, choke coils are cheap for like a 30 horse drive. You're talking like $50 for a choke coil. I mean, it's just an iron core, looks like a transformer. It's just to clean up the voltage. I mean, it's cheap insurance.
Gotcha.
But they will blow up like crazy when they short out.
Well, when you have like just a direct across the line short, is that what you're talking about?
Like inside the actual choke coil itself, it's just like a transformer almost. So inside that choke coil itself, it could have a short. It's got windings in it. So I mean, inside there, like if that thing shorts out, it's like a mini hand grenade. Depending on how big it is, too. The bigger the choke coil, the bigger it is.
Sorry.
So
no. Usually, if you're doing some sort of TD control, you can use the controller to do this. The controller does have to be able to have the refrigerant in there to make sure that it can basically take that pressure and convert it to a saturated. Making sure that the ambient temperature sensor is underneath the coil. You don't want it in the electrical cabinet. I've seen already where a condenser would end up running a higher head pressure because it's doing floating head is basically what a condenser is doing underneath TD control. Basically, has the ambient temperature rises, it raises the basically the pressure that it's trying to maintain, right? But using the saturated condensing temperature. So we had a rack that kept going off on high head, and basically it would do it just randomly. And here to find out, I looked at the ambient temperature sensor and graphed that, and it was getting all the way up to 130 degrees. I'm like, there's no way. And traced out the sensor and find out that it was actually in the electrical cabinet, and electrical cabinet was getting up to 130 because it was within the sun, No one ever programmed a max in the VFD. So basically what happens is, if, like I said before, it's going off of the TD of the actual condenser. So we would need a drop leg pressure transducer mounted on the drop, on the drain leg, and an ambient temperature sensor underneath the coil. But like I said, it has to be underneath the first fan that's on or the last fan that's off, which is basically the one closest to the header. That's so we have air going across that all the time to make sure we're getting an accurate ambient temperature. You can do TD control with an evaporative condenser, but at that point you actually have to do what's called use a wet bulb temperature instead of a dry bulb. Basically, to do that, you need an outside temperature sensor, and you'd also need an outside relative humidity sensor, so you can actually get an accurate wet bulb and figure out what TD you're going to maintain with the wet bulb temperature, because you're using water to basically as the cooling media on the evaporative condenser. Anything you want to add?
No, that was a pretty good explanation on like TD control. Actually, you know what? There is something I want to add. So you're talking about your ambient temp sensor and everything, and your condenser is going to maintain that TD, but there becomes a point where it is no longer efficient to run the condenser off TD, like usually like around like 95 degrees. Like I like to lock on, my fans. So I'm not going over a 95-degree saturation temp because you're not saving any energy there.
Yeah.
You're just putting more wear and load on the rack. So you want to try to desuperheat as much as you can at that point. So usually like 87 to like 89 degrees, I have my own program I use for CPC. Like I lock my outdoor air temp sensor so it can't go any farther, because like in CPC you can't program a max TD or a max SCT set point like you can in Danfoss. So you have to fake out the controller to make a max setting. So that's what I'll do. Like it past like 87 degrees, I run my fans 100%, because you're not really saving any energy. You're just causing it to you cause your head pressure to just get higher and increasing your discharge temps. I mean, most of these condensers are sized on a TD spec, but let's be honest, that TD spec is 95% of the time not right because of the load issues.
Yeah.
I mean, the size for 100%. So, I mean, a lot of times our TDs in supermarkets are a lot lower than what the design is, because you have more condenser than you do compressor. So when it is a little hotter like that, you could afford to run a little. For what you're going to save in horsepower. I mean, do you agree? For what you're going to waste in horsepower, you're probably going to save a little bit on the compressor end at that point.
Or, I mean, you get to a certain point where you just want to start bringing down, the saturated condensing temperature at a max. I believe in E2, like you can actually program. You can have a separate thing feeding it, so you could actually make some sort of sensor control, and you could have a max value in there and not have it feed that way. Here nor there, it's basically, yeah. I agree. Where basically you don't want to go too high. You're not going to keep ramping up higher and higher as the ambient goes. At one point, like I know some customers, they go depending on the refrigerant, right? So some customers will do like a max of about 114 degrees saturated with 407A.
Yeah, that's rough, man. That's high.
I'm in Texas. You know what I mean? Remember that. There are some weeks where you could sit on a condenser and burn your ass. That's how hot it is. So
yeah, I guess that's the difference between sitting on a condenser and freezing to it.
I've been there too, man. I spent about 5 years in Connecticut, man. It's cold, and I know it's cold when you're having to throw bottles of refrigerant in a slop sink just to keep up the pressure so you can actually.
Oh yeah.
I got a couple of pictures where it was minus 27 with the wind chill, and I'm having to wrap plastic wrap on the top part of the shrouds of the condenser fans because I couldn't get the head pressure above 15 pounds on an EnviroGuard. Nothing wanted to move, nothing. And basically, I'm throwing shit in the slop sink to warm it up so I can get refrigerant into it. I'm trying to raise the head pressure, and I'm excited when I got the head pressure finally up to about 75 pounds.
Yeah, that's a whole nother ball game. But yeah, with CPC, for example, Emerson, like there is no max float unless you make some kind of program. It'll just keep going to the moon, till it hits that fast recovery set point and forces everything on to 100%. It'll just keep raising that SCT target to whatever the TD is plus ambient. So I mean that's the only downfall with doing TD with CPC. With Danfoss, you can actually program a min and max set point. So that's where the little issue comes in with CPC. You got to kind of fake out the outdoor air temp sensor to make it work properly.
Like you said, either that or find out what the pressure would be at the saturated condensing temperature and just put that in for your fast recovery set point. That way
but then you got to watch that, because then you're like coming in on a fast recovery like nonstop.
We're in fast recovery once it hits 100 degrees here, so.
Yeah, so we don't have that problem. But so we went over the controller way to control TD, and like the next way to control TD would be actually using the drive itself. Like the drive would be a what would be considered a smart drive. Now, when I say that, I mean like it's got more than just a 0 to 10 volt program in it, like you would get from the controller doing it. So when I say smart drive, I mean it has a predefined PLC program in it, with the refrigerant type and everything else in there. And it is actually doing all the condenser functions itself. Now, the couple benefits to this is it's standalone. So meaning if you lost the controller, this drive will still function and you will still have condenser head pressure control and all that stuff. If the controls go down, you're still that. And I mean, and if the drive goes down, you still have control with the EMS system over the condenser if you need to take it back. So the way this works is it's very similar to the EMS control. You're going to have a temp sensor underneath the condenser. You're going to have a pressure transducer. Now, there's a couple ways to do this. You could have a pressure transducer going to the drive itself. We're going to talk more so about Danfoss and some NIDEX stuff. I mean, most of the stuff I see with smart drives is Danfoss and some NIDEX stuff, but the Danfosses work extremely well. Probably one of the best condenser drives you can get. Very easy to set up. The way they're doing it is they're taking two analog signals. You get your outside air temp sensor, which you'll be using to figure out TD, and they're going to be using your drop leg pressure or your discharge pressure, depending on how the customer has it set up. Now, you could have your own transducer, and the drive could be totally separate, or they could be piggybacking the signal off the EMS system's transducer, meaning like they're grabbing the signal and ground wire, and they're just tapping into it and then sending it back to the drive for an analog input. Now, this drive is figuring out the TD via a bunch of settings inside the drive. It has refrigerant profiles in it, basically, and it has your set points in it, your min and max TD settings, your min and max pressure, your ramp ups and ramp downs. Now, this is going to be controlling your TD and your split functions, depending on the customer. It may be controlling your split. So, I mean, this is a similar thing you're going to see 99% of the time at most Walmarts. Not every Walmart, like some of the newer stores went back to non standalone drives, but most of those Walmart and Sam's stores have these Danfoss drives or a Control Techniques, which is NIDEC now, VFDs, and they're using those to control their condensers. They work extremely well when they're set up properly. Most of the time when you're having issues with them, the setup's not right. And then there's actually a Danfoss setup guide I keep it in my van. I have it on my phone. Like, I use it all the time. And if you follow that guide for them, I mean, those things are pretty much dead nuts on. They kind of offset the set point a little bit to make up for the glide. I think me and you were talking about that the one day, Brett.
Yeah.
How they, you want to go over that real quick?
Yeah. So basically, the drives do not have a dew point and bubble PT chart. They have a dew point. So basically, we're trying to maintain saturated condensing temperature, but, basically of the drop leg. And, because of these high glided refrigerants, either want to use, the bubble point, or for most condenser controls in most manufacturers, they just end up using the midpoint. So in order to do this, in the Danfoss guide for setting up those drives for that particular one, they actually have you pad the TD by about 4 degrees to make up for the, basically the glide of the refrigerant. So if it says on the on the RS schedule, on the refrigerant schedule, that the glide is supposed to be, 15, basically you're to set up for 19, basically just to get a glided value, on there to maintain a better saturated condensing temperature. like I said before, we're going off the ambient temperature sensor and trying to maintain that control. When doing this, we have to make sure. I mean, because we don't know, we could have an ACI, we could have a BAPI, we could have a CPC, we could have a Danfoss, different transducer on there. Making sure that whatever transducer you have, it's actually set up for that particular pressure transducer. I have seen on a NIDEC drive, and this happened once or twice, where the NIDEC drive was basically whenever you change something like a pressure transducer on a NIDEC or an ambient temperature sensor, after you change that parameter for it, you actually have to down power cycle the drive in order to actually have it come up with the right parameter. And a gentleman was having a problem with control when it got 0 degrees when it actually snowed here in Texas for 2 days, and he ended up his pressure transducer was showing 240, but in reality it was only like 76 or something like that. The head pressure was all the way in the toilet, and it was programmed right, but it was showing the wrong pressure. So I said, all right, well, check the program. He did. It was right, and I said, well, program it wrong, power it down, program it right, and then turn it back up. And basically it started running. And basically that's what he ended up doing. And once he got it back programmed, it started working properly. Same thing with the ambient temperature sensor. Make sure that thing is actually programmed right for the proper temperature sensor. For the Walmart program, sometimes they use Novar temperature sensors, or they do use the PT1000s. Anything you want to add?
Yeah, so one thing on those the newer NIDEC drives, you have to have that drive come out with that program in it. If you just say, if you're at one of those Walmart Sam stores and you just order a NIDEC drive, you just go to like some random place to get a NIDEC drive, that drive will not work. You have to get one that's flashed with that program in it. It's not like the Danfosses where you could just back it up off the screen. It has to come with that like set of programs in there.
It's actually called. I literally just went through this today. It's a deep source program, because that's what we got. So Walmart usually goes through Motion Industries for all their NIDEC drives, and that's because Motion Industries actually programs all their drives for them. Well, we gave them a quote. I gave the purchasing department a quote for it, and for some odd reason they ordered the drive from Emerson. I didn't realize. I went out there to go help somebody, and I'm looking for the parameters for the pressure transducer, the ambient temperature sensor, and the refrigerant. I can't find it. It wasn't in there. So now I basically have to rip it back off the wall, box it up, send it to Motion, have them program it, the deep source, and then basically have it shipped back. Because it's not like I could go to another store like with a Danfoss. You can take one display, take that program, put it on the fascia, put it on another drive, and put it on the other one. NIDEC, you can't do it. I think gentleman called it a deep source program, where basically it's deep in in the actual base. You can pull it back up. Like if it loses one part of the program, you can actually pull it back up from the deep source that's embedded in the drive. It's almost comparable, I think, to almost like the Commander SK having the thumb drive, except for this doesn't have a thumb drive that's removable.
Yeah, one quick tip with the Commander SK: do not push that thumb drive in too hard, because it's just a plastic little clip on the backside, and it'll go right through the other side. Been there, done that. You don't want to do that, because then the drive's junk.
No, why'd you do it?
Because I didn't think it went in all the way, and then it went in all the way. It went all the way in. It's supposed to just be the tip of the card in there. So that's a basic overview. Like most of the time, like you're going to see a lot of Danfoss stuff. I mean, the Danfoss drives, you could change the transducers, the temp sensors, like Brett was talking, like on the NIDEC ones. The Danfoss ones, you could change everything but the temp sensor. You could change it to a CPC transducer, a Novar transducer, a Danfoss transducer. All you got to do is change the scaling inside the drive itself. So if you're out and you got a bad transducer at a Walmart on a condenser, and you say it's got a Danfoss transducer on there, or a Novar transducer, and you only got a CPC transducer on your truck for the drive, you could change, as long as that transducer is not also supplying condenser control board. You could just basically take that transducer, put a CPC one in there, and just reprogram it, and that drive will work fine. Same thing, like you just got to watch, like if say the drive isn't working and nothing's working and everything's down. If your discharge transducer shorts out on like a Novar store, they're taking it off the CCM, the condenser control board, and you go up there and you got no DC power feeding, no 24 volt DC power feeding that transducer, and you're not getting the signal supply or ground back, that drive won't work because it's not going to see any pressure. So that's just one thing to be aware of. And I mean, if you do get in that, I mean, you could always, use a 9-volt battery, something like that, to redo it. There's plenty of things you could use to make it work, to make a signal if you don't have a signal generator. Just like a C123 battery is 3.5 volts, which is great for testing IDCM modules. If you want to make a poor man's voltage generator.
Yeah, you could use a battery and a potentiometer too. That works. Basically, what he's talking about is being able to manipulate, the pressure in case, something were to happen with, because, typically you're getting the power of the DC voltage off of the drive. Never cross any kind of AC voltage with the DC voltage that's in there. You're going to end up frying out what's called the rectifier, which basically takes the AC and converts it to DC. Making sure that, if you're ever doing a PM on a drive, making sure that you're blowing out all the, all the heat sinks in the back. Drives create a copious amounts of heat. So make sure that, all the heat sinks, the fans are actually blown out with air with nitrogen. That's going to help prolong the life of the fan as well as the drive. Most drives have 3 contactors in them. All right, usually labeled M1, M2, and M3, and basically M1 is usually the contactor that allows power to go into the drive. Because remember what I said, we're taking AC voltage and turning it into DC voltage, right? So you have a contactor in the beginning that lets voltage go into the drive itself. Basically, then there's another contactor on the outlet, typically M2. And that's going to let the DC voltage now leave the drive and go into the actual motors, and let it have the variable frequency that it wants. They have typically an M3 contactor, which is a bypass contactor. Okay, that is there in case the drive were to fault. Usually on every single drive you have some sort of fault set of relay contacts. And if, God forbid, the drive, you have a condenser fan motor that shorts where it sends an earth ground to, back to the drive, it's going to fault out that drive. It's going to shut it down and not allow it to damage the actual drive. So what it's going to do is shut off the power going out from the drive and then energize the bypass contactor, which is basically in parallel with the VFD. So then instead of, running that voltage through the drive, turning it into DC, it's just taking the AC voltage and driving it right to the condenser fan motors. Anything you want to add to that?
You don't want to ever push the drive bypass contactor in when the drive contactor is energized, or else you're going to have a really loud, explosion, and you're going to let the smoke out of the drive. So you don't ever want to push contactors in when a VFD is, involved, because you need to make sure that you're not going to energize the bypass contactor. Usually there's auxiliary contacts on there to keep one or the other locked out. So if the VFD bypass contactor is energized, the VFD output contactor is electrically mechanically isolated via the auxiliary contacts. So that way one can't energize when the other is energized, because if you do, you're going to have a big smoke show. Those DC rectifiers in the phase gates, basically inside the drive, cannot take that AC power on the other side. It's a potential difference, and it will cause an explosion. So it will. Well, what's that?
I said it can. It'll take it for a second or a half.
Till it doesn't. Yeah.
So typically those are always wired and normally closed. So then that way, if the M2, so you'll have an auxiliary set of contacts on either the side or on the top of one of the contactors, and it'll be a normally closed set of contacts. So like if M2, which is the outlet of the drive, would energize, basically it's going to open the set of contacts that are connected to the coil of M3 to ensure that you physically cannot have M2 and M3 come on at the same time, where you're actually allowing AC and DC voltage together. I just worked with someone the other day, and he's like, yeah, I worked on a drive. He's like, I felt real scared, and the only thing I can remember was Brett said, don't push in the damn contactors at the same time. Don't do it. And I laughed because that's one of the only things he remembered. When we were talking, I was just giving him a quick overview on, safety hits, what not to do with a drive. And that was the biggest one that I always hit home with, because, man, I don't want anyone getting hurt, and if, one of the biggest things is not being educated on something. And that's why I end up, some people end up, getting hurt. They don't know, they don't understand. And, I try to push that home whenever I think that's always usually the first thing I talk about when we start talking about contactors, or about VFDs, where I'm like, hey, first things first, don't ever just assume that you can just push this shit in and then explain why. And then when I say that they'll blow off the wall, they're like, okay, I'm not going to do that.
The other thing you need to be real conscious of when you're working on VFDs is the fact that they have large capacitors in them, and that those capacitors take time to drain down after the VFD's powered down. Just because the screen goes blank and the power goes out for a second doesn't mean that those capacitors are completely dead. There's a bleed resistor inside those capacitors that have to bleed down the capacitor banks inside the VFD, because otherwise they store a charge. And it's not like a capacitor on a residential air conditioner or a fan motor. You're talking capacitors that have enough voltage in them to kill you. So that's one thing to be aware of. I mean, some of those capacitors on some drives, some large drives, it may take up to 10 minutes to discharge them. So just make sure you test with your meter, on the incoming and outgoing voltage, that you actually have no voltage coming, into the drive and out of the drive. So when you're looking at it. So the next thing I want to go over is the two. So using a VFD. So we'll break this down kind of in a, I guess, like an Emerson term, because I think it's a lot easier for guys to understand. So you have like two different types of condenser control when it comes to variable speed. You have like variable speed, where you're just running all the motors. They run in the condenser all together. So those motors are running all. So if you have 12 motors in a condenser, all 12 motors are running together, and the VFD is running the motors up and down, in synchronization together. They're never cycling off. They only all shut off when they all shut off. Yeah, that's pretty standard. A lot of older Walmarts do that with Danfoss drives. It works pretty well depending on the ambient. They'll split the condenser in half and run it like that. But so one thing to really watch out for is, like, if it's really cold out, and this strategy doesn't work as well because you don't really have any fan cycling to back it up. On a properly sized rack, it works really well. Now, the next thing we're going to go over is what I would call, in Emerson calls it Vss Combined. So you're using variable speed and fan cycling combined. So this is like a cooler weather application. So out like by me in Chicago, like it gets super cold out here in the wintertime. So I mean, we can't run 12 fans at the same time. We need to split the condenser in half. Okay, we drop off half the fans. Well, still 6 fans is too many. So what we start doing is the VFD is going to control those fans up to a point, depending on how the PID loop runs inside the controller or whatever's controlling it. And then it's going to start dropping off fans, one by one till it gets to till it gets down. Then it'll start ramping up the drive a little bit and picking up fans as it needs it. So it's trying to control with less fans. This is the most efficient way to control the condenser, but your control algorithm has to be like on point so you don't get this fan cycling and VFD fighting each other. You want them to work in synchronization. So I kind of play with your settings depending on what you have in order to make this work properly. Otherwise, you could end up with a machine gun just constantly cycling contactors on and off. You usually got to play with your settings and to get it to work properly. But like this is like in a cold weather application, I mean, you pretty much need that Vss Combined, the variable speed control along with fan cycling. And area like where Brett is, I mean, you can get a long way with just variable speed probably most of the time, except for, when Texas froze over. I mean, yeah. When they learned about holdback valves.
That's so damn right. So, and I have a question. So we have a way we set up. It's per customer, right? As far as setting head pressure controls with running VFD, because a lot of people are like, oh, well, it's a minimum saturated, so it's never going to go below that. Well, anyone that's lived either, up by you or on the East Coast, I mean, they'll know that. Yeah, you still need the holdback valve. You still need the receiver pressurization valve. What's your threshold? Like, I mean, let's just say you're doing a saturated of 77 for a minimum for a VFD. I mean, I know you like floating the hell out of everything, but I'm saying like if you're doing 77 degrees, for the saturated for that, where are you setting your holdback valve and your receiver pressurization?
So I pretty much go the same number across the board unless it's customer spec to be something else. 70, 60, 55. So fans off or my fan control set point is 70. Okay. Fans completely off at 65. Hold back at 60 degrees and then 55 degrees for my receiver pressurization.
Gotcha.
Rock solid numbers up here. I mean, I keep them tight. I mean, they're tight. I mean, you got to be on your money with how it's set up, but rock solid.
So don't set them up the way.
What's that?
Nothing. Go ahead.
Okay, so that's the VSS combined method for cycling condenser fan motors with this. I mean, most CPC stores you're going to see like that unless they're running those terrible ECM VFD motors, those Gutner not Gutner motors. Impaps. I have an absolute hatred for those things.
They're not bad as long as they're not. So just if no one's familiar with MPAS motors, they can be controlled via a 0 to 10 signal, or they can be controlled via Modbus, where you actually communicate. Yeah, so you can communicate via, the controller can actually talk right to them. I don't mind if they're 0 to 10. They're expensive as hell. I think they're $7 or $8 grand a piece. And so typically nowadays, what anyone does as far as control strategy with those is they'll run them at 100% at 0 volts, and they'll run them at 0% at 10 volts, which is a really smart idea because basically, if you have an analog output, because that's what you're driving it with, right? You're driving with a DC signal, so that's an analog output. If you're driving it with a DC signal and the device that's actually putting out the signal takes a shit, it's okay. It's in the middle of summer. You're just going to run 100%. The first time I ever ran into this was about 10 years ago, and my analog output died. I'm pacing back and forth. I end up having to put a battery on to get it to run. But nowadays, now that they've actually programmed from the factory to be fail safe like that, for that very reason. Kevin hates them because he's had a bad experience with trying to mod bus the things together with having all the noise with them.
No. I've had bad experiences because they can't handle like a drop of rain and they short out and cause massive casualties. So, all right, with the 0 to 10 thing and the 10 to 0, I always, unless it is customer spec, set every condenser up to be 10 to 0. So 10 volts would be condenser full off for that very reason that Brett said, because it's your fail safe. You want everything in refrigeration to fail on. So that's our fail safe. But with the EBM motors, especially the older ones, I've seen like the last 2 condensers I started up that had them, every motor came back to a terminal block, which I think is a lot better idea. So every motor came back to a terminal block in the condenser, and they all got the 10 to 0 volt signal at the same time, which, great idea. The older motors, so what they would do is the lead motors would be 10 to 0 volts. Okay, so they would be 10 to 0 volts. There's a jumper in there. I think it's DI1. If you jump ground to DI1, it changes that motor from 0 to 10 to 10 to 0. Now, what they do is, so they take the lead motor and just jumper it out, and then they go through the relay. So if there's a 10 volt signal in here, which we're going to get to in a second. So they wire the 10 volt signal to normally open. They wire the signal coming out of the AO out from the EBM, the lead EBM motor, to the normally closed, and they wire the next motor analog in to the common. So basically they set this up so if the first motor is going to get its signal from the controller, so the 10 to 0, say it's at 5 volts, okay, it's gonna scale the signal complete opposite. It's going to scale 0 to 10 volts to the next motor. So 0 being full or 0 being off, 10 volts being full. The reason they do this is if the first motor fails, or goes to default, it's going to kick all the other motors to 100%. By when it switches the fault relay, it puts 10 volts to the next motor. I mean, it sounds like a great theory, and when it works, it does work. But if the first motor ground out and the relay fails, or somehow the relay fails, there's no 10 volts going to the next motor.
What manufacturer is doing this? I've never seen that set up.
So Bone, that's how they wire the EBM motors, and that's how EBM wants them done, or wanted them done up until this point. So on those motors themselves, every one of those motors has a 10 volt DC output signal in it. So if you do lose, like, because we had this problem, we had a store where we lost the lead motors and we lost random motors. We ended up losing like 12 of them in a year because of water issues and other issues with lightning strikes. So if you were to lose the actual like analog output module, so I was able to rewire a motor just to, MacGyver it, but B, you could jump ground to or AI1 to 10 volts and all the motors, and they'll take off around 100%. They have their own 10 volt signal inside of the motor itself.
Basically, those impasse motors, if no one's ever seen them, it's basically every single motor has its own individual little drive on there. That's why they're usually $7 or $8 a piece. And what we're talking about, so when we first started the podcast, we were talking about, VFDs that are basically, self-contained, you know what I mean? Where they don't require any external signal. Basically, they're making up however what they want the fans based off of, the pressure transducer and the ambient temperature. Now, the way that we're, talking about things, we're actually sending some sort of signal from, whether it be Danfoss or I keep wanting to say Control, E2, RDM, basically, scaling that out. Sometimes, so RDM right now, in conjunction with Zero Zone, what they're doing is they're actually, I don't know enough about the RDM programming, but I know that, they are setting a 0 to 10 volt signal. out to their stuff. But what they do is they actually use a converter board, which basically takes the 0 to 10 and reverses it, and sends it out 10 to 0. So in case something would happen with the analog out, it's still sending out that voltage to those motors to run at a certain hertz. Have you ever seen a drive, Kevin, where it actually is sending out more than 60 hertz, or it's actually sending out 100 hertz and there's no rhyme or reason for it?
Like it's not programmed to do it?
No, it is programmed for it, but something in the drive is just telling it that we had one that was delivering, I think, 580 volts out to these condenser fan motors, and it was programmed right. I think something just snapped in the drive where it just wouldn't. It wasn't going to 60 hertz anymore. It was going to, I think, 90 hertz or 100 hertz or something like that. It was something ridiculous where we had all these condenser fan motors basically start going off on internal overload because it was just way too much heat draw on it.
Yeah, I mean, I've never seen one where it wasn't programmed to do it, but I mean, everything could fail. I mean, I've seen them where they've potentially ran thing. We had a condenser where it was designed to run at 70 hertz. Like they would essentially they essentially would run faster. It's the way it was designed. But yeah, I mean, anything can fail.
So remember when?
So go ahead.
Oh, what I was going to say is we have, there's always usually some sort of enable, whether it be an enable and a forward command. We basically have to have three things for a drive that, we have to have the voltage going to the drive. We have to have some sort of signal, whether it be generated off its own or a 0 to 10 or 10 to 0. And we also have to have a run command. We have to have some sort of relay output on our BAS system. You'll hear me say BAS every so often. It's a building automation system. So, just to cover all the basics. Basically, you have to, just tell it that, hey, you're ready to go. Otherwise, a lot of the drives will say inhibit or not ready. This is usually done by jumping 2 or potentially 3 sets of contacts on a particular drive. I believe, correct me if I'm wrong, Danfoss's enable, it was at 52, 53.
I believe so, yeah.
Yeah. So basically, you have 24 volts DC coming off the drive, and you're basically just using an external set of contacts from your BAS system to basically close that set of contacts to say, hey, yes, I in fact am calling for the drive and I want you to run. You know what I mean? Because, you might be setting 0 volts to it, which might tell it to run 100%, but until you actually enable the drive, it's not going to do anything. Sometimes a lot of these smart drives that he was referring to too also, control other functions like you were stating before, like controlling the split. Danfoss has what are called comparator values. I don't understand how they basically convert to a pressure. Because like for a comparator value for 407, so it splits at 138 or something like that is set for 24. Doesn't make any rhyme or reason. It's something deep in their program that they're using that what they call a comparator number. That's basically telling it when it wants it to, when it wants it to actually split and unsplit. You also have a fault set of contacts usually on every single drive. So in case something happens, especially if it's a singular drive where it's working on its own, can tell the BAS system, hey, I got a freaking problem. You need to do something else. And that's usually when you energize that bypass contactor that we were talking about before. With the enable, though, back to that real quick. Sometimes it's not just closing 2 sets of contacts. Sometimes you are 1 set of contacts. Sometimes you have to basically jump potentially 3 sets of wires together, because some drives have a forward and reverse command with them. So if you were enabling, I think NIDEC has forward and run enable that you'd have to jump together with the 24 volts DC that's actually on the drive to actually make it, ready, where it doesn't say inhibit, where it's actually not ready. Got anything else, Chief?
Yeah. One thing I want to go over with those M400 drives. So, I mean, we're going to go over this certain customer because this is where I see it all the time and it really messes guys up. So at an Aldi, they have these cookie cutter drive setups. They use M400 drives with a bypass cabinet. So this is a situation that I run into quite often, and it's very easily avoidable, and it messes guys up. So at these Aldis, they have the condenser control board controlling the bypass contactor and drive contactor, output contactor. Now it's on the same output. It's output number 8. Dip switch should be down. This happens all the time. Guys force the dip switch or something else. Okay, but what happens is there's a fuse in there for the CPC board, obviously. After a power outage, this happens all the time. I don't know why, but the drive bypass contactor will short out. I've never seen the drive output contactor short out. It's always a drive bypass contactor. But what ends up happening is guys try to jump out things to get it to work. Well, they need to replace the fuse and unwire the drive bypass contactor out coil wire in order to get it back on, because if the drive, the way they wire these in, these are semi-smart drives that Modbus, they're getting a Modbus signal from the E2 to tell it to run, how fast to run, if there's a fault. All that comes in from the E2. None of it's a hard fault signal. So one thing you want to watch out for is, yeah, you may be telling it to run on the E2, but the forward run enable is still hardwired through the bypass contactor auxiliary. So if the bypass contactor is pulled in, it will drop out the drive enable. So this is one thing that messes guys up. They'll try to bypass things, but until you get that contactor for the drive pulling back in and it dropping out the other contactor, it's not going to. So that's one thing to keep in mind. I don't know why 208 coils seem to fail a higher rate. You ever notice that, Brett? 208 coils, after power outages, just shit the bed, but 120 volt ones hardly ever do.
Because you run the potential of single phasing, right? You're not necessarily always getting back both the phases, right? You have a higher probability of missing a phase. So that's what makes sense to me anyway.
Yeah, I just it's always something I always kind of wondered about, because you ever notice we have stores up here after power outages. I've had 40 contactors burn out at once. But then you go to a store, it's got 120, and it's got original contactors, some of them.
Yeah, like I said, it's probably because how many times have you seen where you get a store back and things start lighting up, and then everything sounds because you're basically only getting 2 out of 3 phases. You know what I mean?
Sounds like money.
Yeah, no, absolutely. I'm not saying it doesn't. Also sounds like a late ass night. We had a store, when Sandy hit, when Hurricane Sandy hit, when I was on the East Coast, and we got flooded the hell. And in Connecticut, there's a lot of little towns and stuff that are right on the shore and stuff, and it just so many generators all over the place. People not ordering the right size generator. I had a guy at a small grocery store was trying to run his store off of a welding generator. He had a small SJ cord, probably 8 gauge running to the contactor. I'm like, is this for your lighting? He's like, no, that's for the rack. I'm like, that's not going to work. The best is when you have a large box store, like some sort of club store. And you're there, and all of a sudden, you're testing everything on the generator. Everything's working fine, and then big ass panels start going to defrost. And all your shit shuts down because you're basically going from 480 down to maybe 390 because everyone made sure that it was big enough to run the rack. Totally forgot about the electric defrost, or you get a generator big enough.
Yeah.
or you get a generator big
We've had
enough
the same thing happen.
and not have a big enough diesel tank for it, so it runs out in 4 hours.
Yeah, it's not good. Yeah, it's not good. But that was a like a brief explanation on how like the condenser drives work. I mean, we'll go quick into like compressor drives real quick. I mean, we're not going to spend like that much time on it. It'd be like another podcast probably. But so with like compressor drives, so we're using a VFD to control the compressor speed, basically to control our saturated suction temperature, to keep it steady. The steadier we keep the suction saturation, the better the rack runs, the less cycles we have. So a VFD is a great option. It's honestly probably one of the best options to control your suction pressure on a rack. It's going to give you the smoothest control out of anything. I mean, a digital compressor is great, but it's choppy. Where you have like the loading and unloading. You don't get that with a VFD. You get nice, smooth operation. The only problem with VFD is you're fixed on how fast or how slow you can go via the compressor speed, because a piston-driven compressor is a constant torque compressor. So your torque isn't changing like a fan motor would. Like you can't vary your torque. A compressor is a fixed torque compressor. So like once you get down to a certain amount, it needs that amount of torque in order to move that compressor still. Most compressors are like, obviously it's 0 to 6, it's 30 to 60 hertz. Some compressors will let you go down to 25. So you get that range in there. So I mean, you don't have as much range, but if you size the compressor properly, you won't have an issue. Along with some unloaders and some other compressors, you won't have issues. But I mean, we're doing basically the same thing, except the PLC, CPC, Danfoss, Novar, Comtrol. I don't know why I'm saying Comtrol now. Thanks for that.
EIL, ECI.
No, we didn't have any of that stuff. So that'll be controlling that compressor. I mean, you could have a bypass set up. It depends on the customer whether they have one or not. I mean, you should. I mean, but that compressor is controlled off a 0 to 10 volt signal or a 10 to 0 volt signal, depending on how it's set up. And it's going to be controlling via your suction group is going to be sending that control to it. Now, some things you got to watch for, obviously, is oil pressures. You don't want to be at the bottom range of your run, the entire time. You could make some oil issues. But a VFD is generally going to be the best option because you could start it at a lower hertz. It's going to be softer on startup. I mean, it's a great option to control your compressor capacity. I mean, is it the cheapest option? Absolutely not. You could do a digital compressor for half the cost of what a VFD could. Head swap. So, I mean, your payback's going to be a little bit longer, but in the grand scheme of things, is it a better option? I think so. I'd rather have a VFD. I mean, it's a lot smoother.
Some of the other things, like you said, besides, because we do have two types of compressors that can go on VFD, right? We have one that has its own oil pump on there, and we also have, basically it's a sling compressor, comparable to a Copeland K body. Bitzer makes one that basically has an impeller in there, and basically slinging around all the oil to all the crank and the crankshaft and all the pistons and rods. On top of usually not liking any compressor at all, liking any liquid. Anything driven with a VFD really, really hates liquid. Typically, like I said before, 20 degrees is what I typically like to see for a minimum amount of superheat going to that Victor rack. I have seen 15, especially when you have systems with short runs where basically the rack's right on top of right where the cases are. You better have at least 20 degrees of superheat if you're running a VFD compressor, because basically you're slowing down that compressor, right? And you run the risk of, compressing that vapor a lot longer instead of having that additional heat of that thing running real fast and actually, maybe helping vaporize some of that liquid with some of the heat from the compressor. So make sure that your liquid situation is under control, or you will be replacing that compressor. Make sure you're just make sure you have like I said, 20 degrees of superheat at a minimum at all times. And like you said before, making sure that the your oil pressure doesn't start suffering from that. One of the other things that can happen with having a VFD, because a VFD can actually basically make the motor spin one way or another. I've seen already where you'll have the VFD compressor running and then another compressor will run, and there'll be some nasty vibration going on and could potentially break some lines. And that's usually due to harmonic imbalance. When you're running, one motor one direction, three-phase motor one direction, another three-phase motor another direction, they're directly 180 degrees out of phase, sine waves. So basically, what happens is you have this internal vibration that goes along throughout all the piping and stuff, which could potentially break suction headers and other types of piping connected to the machine.
Yeah, one thing I want to go over with that, like that is one thing that causes that. There is at times, because I remember me and you went over this, and I've been to several racks where contractors have tried to like clamp the living shit out of discharge headers. Like I went to one and it had like 5 cush clamps in like a 2-foot spot where it kept breaking discharge lines. Okay, so we checked all the phasing. They were all phased the same. They were all going the same way. Certain compressors get harmonic vibrations at certain frequencies. Now, these drives are great. They're advanced. You could delete frequencies out of drives and make it skip. So, like I go through these stores. I do this all the time on CO2 stores. I'll be tuning them. I see it more so on CO2 stores than I do anything else. On the bitzers, like I'll be going through and like say I'll go through a point of a frequency at a time. It may take me an hour to do a compressor, but say at 47.5 hertz, it starts vibrating and making noise to 48.3 hertz. I'll take that frequency range out of the drive. You can go in the drive and tell it to skip that, and it'll skip that frequency when it's maintaining. It's great. It instantly stops the problem if you don't have one out of phase, and it's an easy way to stop issues like that.
Yeah, I think we covered pretty much everything with drives, and there is more stuff that we could cover, but I mean we'd be talking for hours. So what do you think?
Yeah, I mean I'd like to on a different episode get into some like drive troubleshooting. Maybe the next one we'll get into drive actual troubleshooting and go through like how we actually go troubleshoot these things.
All right, man.
So, but that was a good one. Thanks for listening, guys. Have a nice night.
All right, guys. Thanks again.